An astronomical event is coming that will stun the world. Scientists confirm the tiny star system T Corona Borealis is a ticking time bomb, gaining material and energy for an immense explosion. In 2024, this blaze star will suddenly erupt, briefly blazing brighter than every other night sky object for a few days only. This incredible cosmic flashbulb will be easily visible around the globe. But this brilliant burst may be a terrifying omen of a threat far beyond our universe. Let's dive in. Understanding novae and recurrent novae. This blaze star may seem like a harmless cosmic fireworks show. But the truth is, T Corona Borealis hides an unexplained mystery deep within its core. As it prepares to erupt, could this tiny star system be a warning sign of something far more ominous lurking in the vast unknown? In the vast expanse of our galaxy, amidst the swirling constellations and the glow of distant suns, lies a fascinating and somewhat mysterious phenomenon known as a nova. These celestial events, while not as cataclysmic as their more violent cousins, the supernovae, offer an incredible show of cosmic fireworks that can illuminate the night sky with sudden brilliance. Novae, particularly recurrent novae like T Corona Borealis, are not just stellar phenomena. They are cosmic puzzles that have intrigued astronomers for centuries. To truly grasp the nature of a nova, it's essential to understand what it is, and how it differs from other stellar explosions, most notably supernovae. A nova occurs in a binary star system, two stars orbiting a common center of mass, where one of the stars is a white dwarf, a dense remnant of a star that has exhausted its nuclear fuel. The white dwarf, in its stellar retirement, leads a parasitic existence, siphoning material from its companion star, usually a main sequence star or a giant. This material, mostly hydrogen, accumulates on the white dwarf's surface, where the intense gravity and heat trigger nuclear fusion reactions. The result? A sudden, explosive release of energy that causes the white dwarf to brighten dramatically. This brightening is what we observe as a nova, but with T Corona Borealis about to blow up and shine bright, the big question is, could this strange event reveal secrets about the mysteries of the universe? Now you might wonder, how would this nova outburst differ from a supernova? The distinction lies in the scale and consequences of the explosion. A supernova is the terminal explosion of a star, resulting in its complete destruction and the release of an enormous amount of energy, often outshining entire galaxies and producing most of the universe's iron and heavier elements. In contrast, a nova is a surface phenomenon that doesn't destroy the white dwarf, allowing it to potentially repeat the process if enough material accumulates again. Let's dive into what truly sets recurrent novae apart, and what makes T Corona Borealis so special. In short, it's their predictability and rarity. Recurrent novae are systems where the nova event repeats itself due to the continual accretion of material onto the white dwarf. Unlike classical novae, which might burst once and never again, recurrent novae like T Corona Borealis flare up at intervals dictated by the mass transfer rate in their binary systems. This predictability makes them invaluable to astronomers who study the mechanics of accretion and the evolution of binary star systems. Imagine a universe where celestial clocks tick with the regularity of white dwarfs accumulating matter, only to release it in brilliant bursts of light. This clockwork regularity is rare in the cosmos, making T Corona Borealis and its kin subjects of intense study. How often does this stellar spectacle occur? For T Corona Borealis, the intervals are about 80 years, a blink of an eye in cosmic terms, but a lifetime in human terms. Each outburst offers astronomers a fresh opportunity to peer into the processes that govern stellar evolution and binary star dynamics. But why should we, as mere observers on Earth, care about these distant fireworks? Here's a compelling reason. Understanding novae helps us grasp the fundamental processes that govern the universe. The material ejected by novae enriches the interstellar medium with heavy elements, which in turn can form new stars and planets. Some of the atoms in our very bodies were likely produced in such stellar explosions. Moreover, studying these systems allows scientists to test theories of how matter behaves under extreme conditions, providing insights that no laboratory on Earth can replicate. And there's an even more intriguing aspect to consider. Could the study of recurrent novae like T Corona Borealis help us predict or understand similar systems that might pose a threat to Earth? While the distances make any direct impact extremely unlikely, the energetic phenomena associated with novae, like high-energy radiation and cosmic rays, could influence our planet's space environment in ways we are just beginning to understand. But what if these cosmic outbursts are more than just firework displays? What if they are warnings from the universe itself about dangers lurking far beyond our celestial neighborhood? The 80-year cycle and current observations. In a shocking revelation, the scientific community has uncovered terrifying evidence that the mysterious blaze star, T Corona Borealis, is gearing up for another devastating explosion, one that could shake the cosmos to its core. This recurrent nova ignites in a catastrophic outburst roughly every 80 years, and the latest data suggests we're next in line for a cosmic front-row seat in early 2024. Why do astronomers believe that TCRB is about to light up the night sky once again? Well, the signs are undeniable. Recent observations have shown an increase in activity around TCRB, suggesting that the white dwarf and its companion star are aligning once more for another explosive event. The material being pulled from the red giant companion has been accumulating at an accelerated pace, as detected through spectral analysis that shows heightened hydrogen absorption lines. This is a clear indication that the white dwarf is gorging itself on the fuel necessary for its next cataclysmic explosion. How does this technology help predict when TCRB might explode? By monitoring the light spectrum emitted by the system, astronomers can literally watch the nightmare scenario unfold in front of their eyes, noting subtle changes in the intensity and position of emission lines. These changes are indicative of the conditions within the white dwarf's accretion disk, the ring of material spiraling into the white dwarf. As the material density increases, so does the likelihood of reaching the critical pressure and temperature needed to trigger the nova. These spectroscopic readings are complemented by photometric data, which measure the brightness of the star over time. An uptick in brightness serves as the ultimate omen that the high-energy hell is about to be unleashed upon the unsuspecting universe. T Corona Borealis is no ordinary star. It's a celestial time bomb counting down to devastation. This recurrent nova has fixated astronomers with its predictable yet terrifying cycle of explosions every 80 years. This unique star system, consisting of a white dwarf and a red giant, has had documented explosions in 1866 and 1946. Now, as we approach the 80-year mark since the last event, overwhelming evidence signals that another outburst is imminent. But this upcoming cosmic detonation could be the most destructive yet. If predictions hold true, T Corona Borealis will suddenly erupt from a faint 10th magnitude object requiring binoculars to see into a blinding 2nd magnitude star blazing brighter than the night sky's most famous luminaries. For a terrifying few days, this eruption will offer a haunting observational window into the violent death throes of an exploding star system. The brief yet brilliant nova may finally reveal key mysteries about the catastrophic forces driving the recurring death cycles of binary stars. The 80-year cycle of TCRB is particularly intriguing due to the dynamics of its binary system. The red giant continuously loses material from its outer layers, which then accumulates on the surface of its companion white dwarf. This material builds up until the pressure and heat trigger a thermonuclear explosion, resulting in the nova we observe from Earth. The cycle is driven by the mass transfer rate between the two stars and the efficiency with which the white dwarf can accrete and compress the incoming matter. Moreover, this impending celestial grenade may pack an even bigger blast than expected. Recent findings reveal not just one, but potentially two magma chambers lurking beneath the surface, adding a whole new level of complexity to the situation. The primary chamber, known since the 1980s, pales in comparison to the monstrous secondary chamber discovered more recently. Imagine a hidden reservoir of molten material just waiting to fuel future eruptions. Finally, satellite observatories like the Hubble Space Telescope and Gaia are our lifelines in monitoring this impending catastrophe. They provide vital, unadulterated data free from atmospheric distortions, painting a clearer picture of TIRB's behavior and its position in the cosmos. Gaia, on its mission to map the Milky Way in 3 dimensions, is giving us precise measurements of stellar positions, distances, and movements, painting a clearer picture of TCRB's antics in the galaxy. Now let's confront the sheer gravity of what we're facing. If predictions hold true and TCRB erupts in 2024, we're not just witnessing a cosmic event. We're witnessing a real-time laboratory for understanding the cataclysmic mechanics behind it. Astronomers are bracing for what may be the most critical live observational event in decades, dissecting the explosive death throes of a binary star system. Historical observations of TCRB. As we brace for the impending cataclysm of TCRB's potential nova outburst, let's rewind to the shocking historical eruptions of 1966 and 1946, revealing the terrifyingly unpredictable nature of this binary star system. The first well-documented eruption of this star occurred on May 12, 1866. Irish astronomer John Birmingham, an enthusiastic amateur sky watcher, noted a sudden brightening in the constellation Corona Borealis. Overnight, TCRB transformed from a star barely visible even through telescopes to one of the brightest objects in the night sky. This 1866 outburst set the stage for TCRB's recognition as a recurrent nova, though it would take another 80 years to confirm this categorization. Fast forward to 1946, and the role of amateur astronomers becomes even more pronounced. On February 9th, Leslie Peltier, an American amateur astronomer, renowned for his contributions to comet and variable star observations, witnessed and recorded the second great outburst of TCRB. His meticulous observations provided invaluable data that helped astronomers confirm the recurrent nature of TCRB's nova episodes. Peltier described the event as an awe-inspiring change, noting the star's rapid brightening over just a few nights. The involvement of amateur astronomers like Birmingham and Peltier in tracking these events underscores the crucial role that these individuals play in the field of astronomy. Amateurs often serve as the vigilant eyes of the sky, providing the first alerts to changes that might otherwise go unnoticed by the professional community due to the vastness of the space and the multitude of stars under observation. But what exactly happens during these outbursts? At the heart of TCRB's system is a white dwarf, a stellar remnant that marks the final evolutionary state of stars not massive enough to end their lives in supernovae. This dense object is typically about the size of Earth, yet contains the mass comparable to that of our Sun, leading to a gravitational field so intense that it can strip material from its companion star. White dwarfs are essentially the exposed cores of former stars, having shed their outer layers and ceased nuclear fusion, now cooling over billions of years. However, in binary systems like TCRB, their story takes a dramatic turn. Orbiting this white dwarf in TCRB is a red giant, a star in a later stage of its life having exhausted the hydrogen in its core. This causes the star to expand dramatically, increasing its radius and decreasing its surface gravity. The outer layers of a red giant are thus only loosely held by gravity and can easily be influenced by external forces, such as the gravitational pull from a nearby companion, like the white dwarf in TCRB. So, how does material from the red giant end up on the white dwarf? And what leads to a nova explosion? The process begins with the red giant's expansion, which brings its outer layers close enough to the white dwarf to be affected by the dwarf's strong gravitational pull. This results in a stream of material being transferred from the red giant to the white dwarf. This material accumulates on the surface of the white dwarf, forming an external layer of hydrogen and other elements. As this layer grows thicker, the pressure and temperature at its base increase due to the intense gravity of the white dwarf. Eventually, the conditions become right for hydrogen fusion, the same process that powers the Sun and other main sequence stars. However, on the white dwarf surface, this fusion occurs all at once rather than steadily. This sudden fusion causes a thermonuclear explosion, which we observe as a nova. This explosion blows away the accumulated material, briefly causing the white dwarf to increase in brightness dramatically, and in the case of TCRB, making it visible to the naked eye from Earth. As we look toward the expected 2024 outburst, the historical data from 1866 and 1946 become even more significant. These records not only provide benchmarks for current scientists to predict and prepare for the next event, but they also continue to inspire a new generation of amateur astronomers to keep their eyes on the stars, ready to witness and perhaps discover something previously unseen. Scientific significance of the 2024 outburst. Now, what exactly do astronomers hope to learn from this event? One of the primary objectives is to deepen our understanding of stellar evolution. By studying how TCRB behaves during its outburst, scientists can refine models of how stars evolve over time. This includes examining the processes of mass transfer between the white dwarf and its companion star, as well as the dynamics of the accretion disk, the swirling ring of material surrounding the white dwarf. These insights not only enhance our understanding of TCRB specifically, but also contribute to broader knowledge about the life cycle of stars in binary systems. Furthermore, the 2024 outburst presents a unique opportunity to observe the process of mass accretion onto the white dwarf in real time. As material from the red giant companion accumulates on the white dwarf's surface, it forms an accretion disk, a swirling disk of gas and dust around the white dwarf. By studying the dynamics of this disk during the outburst, astronomers can refine their models of how mass transfer occurs in binary systems and how it influences the behavior of the stars involved. But the scientific significance of the 2024 outburst extends beyond just understanding the mechanics of binary star systems. It also offers insights into the broader process of stellar evolution and the fate of stars like the white dwarf in TCRB. One key aspect astronomers are interested in is the role of novae in the production and distribution of elements heavier than hydrogen and helium. During a nova outburst, the intense heat and pressure generated by the thermonuclear explosion trigger nuclear fusion reactions, converting hydrogen into heavier elements like carbon, nitrogen, and oxygen. These newly synthesized elements are then expelled into space, enriching the surrounding interstellar medium with material that will eventually form new stars, planets, and even life. By studying the chemical composition of the material ejected during the outburst, astronomers can gain insights into the nucleosynthesis processes at work in novae and their contribution to the galactic chemical enrichment. This knowledge not only enhances our understanding of stellar evolution, but also sheds light on the origins of the elements that make up our own bodies and the world around us. But perhaps the most intriguing aspect of the 2024 outburst is its potential long-term implications for the white dwarf in TCRB. As material continues to accrete onto the white dwarf surface with each successive outburst, it gradually increases the white dwarf's mass, a process known as mass growth. Eventually, this mass growth could push the white dwarf to the brink of a catastrophic event known as a Type Ia supernova. In a Type Ia supernova, the white dwarf exceeds a critical mass threshold called the Chandrasekhar limit, triggering a runaway thermonuclear explosion that completely destroys the star. These supernovae are of particular interest to astronomers because they serve as standard candles, objects of known luminosity, used to measure cosmic distances and study the expansion of the universe. The 2024 outburst of TCRB provides astronomers with a rare opportunity to study a white dwarf on the brink of reaching the Chandrasekhar limit. By monitoring the mass growth of the white dwarf over multiple outbursts, astronomers can gain valuable insights into the conditions that lead to Type Ia supernovae and refine their models for predicting these explosive events. But what does this mean for the future of our universe? Could TCRB be a ticking time bomb destined to end its life in a spectacular supernova explosion? While the chances of such an event occurring in the near future are slim, the study of TCRB and similar systems offers valuable insights into the ultimate fate of stars, like our own Sun, and the role they play in shaping the evolution of galaxies. Similar astronomical phenomena. From recurrent novae to cataclysmic supernovae, there are numerous astronomical phenomena that offer valuable insights into the potential fate of TCRB and the likelihood of it undergoing a nova outburst. One such star is RS Ophiuchi, located in the constellation Ophiuchus. Like TCRB, RS Oph is a recurrent nova with a white dwarf and a companion star in a tight orbit. In 2006, RS Oph experienced its latest outburst, providing astronomers with a wealth of data on the behavior of recurrent novae. However, what sets RS Ophiuchi apart is its shorter recurrence period, with outbursts occurring approximately every 15-20 years compared to TCRB's 80-year cycle. By studying events like the 2006 outburst of RS Oph, astronomers can gain valuable insights into the mechanisms that drive these explosive events and refine their models for predicting future outbursts. But RS Ophiuchi is just one example of the many recurrent novae scattered throughout the galaxy. Each of these systems offers its own unique insights into the processes that drive nova explosions and the evolution of binary star systems. By studying a diverse range of recurrent novae, astronomers can piece together a more complete picture of the underlying physics at work. Another celestial event worth mentioning is the recent discovery of a nova in the nearby Andromeda galaxy known as M31 N2008-12A. This nova, which was first detected in 2008, has provided astronomers with a rare opportunity to study a nova explosion in a neighboring galaxy. By analyzing the properties of M31 N2008-12A and comparing them to those of novae in our own Milky Way, astronomers can gain insights into the similarities and differences between nova explosions in different environments. But recurrent novae are just one piece of the puzzle. To truly understand the potential fate of TCRB, we must also consider the broader context of stellar evolution and the life cycles of stars. Enter supernovae, the most powerful explosions in the universe, and the ultimate fate of massive stars. Supernovae come in two main flavors, Type 1 and Type 2. Type 2 supernovae occur when massive stars reach the end of their lives and undergo gravitational collapse, triggering a catastrophic explosion. These explosions release vast amounts of energy and scatter heavy elements throughout the cosmos, enriching the interstellar medium with the building blocks of future stars and planets. On the other hand, Type Ia supernovae are thought to occur in binary star systems where one star is a white dwarf. As material accumulates on the surface of the white dwarf, it eventually reaches a critical threshold where the conditions are ripe for a thermonuclear explosion. So, what can we learn from supernovae that might shed light on the behavior of TCRB? For starters, the conditions leading to a Type Ia supernova are remarkably similar to those in a recurrent nova system like TCRB. Both involve the accretion of material onto a white dwarf, albeit on vastly different time scales. By studying the mechanisms that lead to Type Ia supernovae, astronomers can gain valuable insights into the processes at work in recurrent novae and refine their models for predicting future outbursts. But the story doesn't end there. There are other celestial phenomena that offer tantalizing clues about the potential fate of TCRB. For example, recent studies have shown that some white dwarfs may undergo a process known as carbon detonation, a runaway nuclear reaction that occurs when the temperature and density of the white dwarf's core reach a critical threshold. This process could potentially lead to a nova-like explosion, albeit on a much larger scale than those observed in recurrent nova. Furthermore, recent advances in observational techniques have allowed astronomers to study the remnants of past nova outbursts in unprecedented detail. By analyzing the chemical composition and structure of these remnants, astronomers can piece together the history of past outbursts and gain insights into the long-term evolution of recurrent nova systems like TCRB. All in all, the study of other celestial events, such as recurrent novae, supernova, and carbon detonations, offers valuable insights into the behavior of TCRB and the likelihood of it undergoing a nova outburst. By drawing parallels between these different phenomena and refining our models for predicting future outbursts, astronomers are paving the way for a deeper understanding of the dynamic and ever-changing nature of the cosmos. So, as we eagerly await the next act in the cosmic drama of TCRB, let's not forget to look to the stars and marvel at the wonders they reveal about the universe we call home. How to observe TCRB. As we eagerly anticipate the celestial spectacle of T Corona Borealis lighting up the night sky with its anticipated outburst in 2024, many are wondering how they can catch a glimpse of this cosmic event themselves. Fortunately, observing TCRB doesn't require advanced astronomical equipment or specialized knowledge, just a sense of wonder and a willingness to look up at the stars. But where should you look in the sky to spot TCRB? The constellation Corona Borealis, where TCRB is located, is easily identifiable by its distinctive semicircular shape resembling a crown. To find it, first locate the prominent constellation Bootes, which lies to the northeast of the constellation Corona Borealis. TCRB is positioned just to the northwest of the brightest star in Bootes Arcturus. With this reference point in mind, you can scan the area around Arcturus with the naked eye or binoculars to locate TCRB. But when is the best time to observe TCRB? The outburst is expected to occur sometime in early 2024, with peak brightness likely to occur over a period of a few days. During this time, TCRB will be visible in the night sky from both northern and southern hemispheres, making it accessible to observers around the world. To maximize your chances of seeing TCRB at its brightest, try to observe during clear, dark nights away from light pollution, and be sure to check the local weather forecast for optimal viewing conditions. Now let's talk about equipment. While TCRB will be visible to the naked eye during its outburst, using binoculars or a small telescope can enhance the viewing experience and allow you to see more detail. Binoculars with moderate magnification, about 8x to 10x, and a wide field of view are ideal for scanning the sky and locating TCRB amidst the surrounding stars. For those with access to a telescope, even a small instrument with a modest aperture of about 2 to 4 inches can reveal additional features of TCRB, such as its changing brightness and any surrounding nebulosity. But what if you don't have access to binoculars or a telescope? Don't worry. TCRB will still be visible to the naked eye during its outburst, albeit as a faint point of light. Simply find a dark, open area away from artificial light sources, allow your eyes to adjust to the darkness, and look towards the constellation Corona Borealis. With a little patience and persistence, you may be rewarded with a glimpse of TCRB shining brightly amidst the stars. Future of TCRB and similar systems. While the upcoming outburst will undoubtedly captivate astronomers and stargazers alike, the story of TCRB is far from over. So what lies ahead for TCRB and similar systems, and what can ongoing research into recurrent novae tell us about the universe? One possibility for the future of TCRB is a period of relative quiescence following its 2024 outburst. After expelling the accumulated material and undergoing a temporary increase in brightness, TCRB may return to its pre-outburst state, with the white dwarf and its companion star resuming their orbital dance. However, this period of calm may be short-lived as the cycle of mass transfer and accretion continues, eventually leading to another nova outburst in the distant future. But what factors influence the timing and frequency of nova outbursts in systems like TCRB? Ongoing research into recurrent novae seeks to answer this question by studying the dynamics of binary star systems and the mechanisms driving mass transfer between the white dwarf and its companion star. By monitoring the behavior of TCRB and similar systems over multiple outbursts, astronomers can identify patterns and trends that shed light on the underlying physics at work. One area of particular interest is the role of the white dwarf's magnetic field in regulating the accretion process. Magnetic fields play a crucial role in shaping the behavior of accretion disks and can influence the rate at which material is transferred onto the white dwarf's surface. Understanding the interplay between magnetic fields, mass transfer, and nova outbursts is key to unraveling the mysteries of recurrent novae and predicting their future behavior. But TCRB is just one piece of the puzzle. Across the galaxy, numerous other recurrent novae await discovery and study, each offering its own unique insights into the nature of binary star systems and the dynamics of stellar evolution. By expanding our catalog of recurrent novae and analyzing their properties, astronomers can build a more comprehensive understanding of the factors that govern nova outbursts and their impact on galactic ecosystems. Recent advances in observational technology, such as the advent of wide-field surveys and high-resolution spectroscopy, have revolutionized our ability to detect and study recurrent novae. These powerful tools allow astronomers to monitor large numbers of stars simultaneously and capture detailed spectra of their emission lines, providing valuable data on temperature, luminosity, and chemical composition. Thanks for watching another episode. Click the next video on your screen for more.